Hello there, Mr. Sutton here, bringing you the AB Calculus 2.7 homework solutions on Intermediate Value Theorem. For this problem, we're asking if the IVT shows the existence of a c such that f of c equals 0 for this function on the interval from 0 to 2. So with IVT, we always have to double check to make sure we have continuity for this function on the interval. So between 0 and 2, are there any discontinuities for this function? Well, there are. At x equals 1, we have an infinite discontinuity. Since we have a discontinuity on the interval, the IVT can't guarantee anything and does not apply on this problem. For this problem, we have a little bit of an oddball problem here. We're asking if the IVT shows the existence of a c such that f of c equals 2 for this crazy piecewise function on the interval from -1 to 5. Let's start by checking for continuity on the interval. So let's see what rule this even falls in. This rule from -1 to 5, this is all stuff that is greater than -2. So this falls completely in this second rule. And looking at the second rule, the whole second rule is continuous because it's a polynomial. So that means that we're definitely continuous on this interval. Now we kind of lucked out here because if this had been kind of overlapping between these two rules, we would have had to have checked for a jump at this border value of -2. But since it's on this second rule, we can just go straight ahead to seeing if the y value 2 is between the beginning and ending y values for this second rule. So let's plug in our x values. -1, if we plug that in here, that's going to be 1/2 minus 1, which is -1/2, -0.5. And if we plug 5 into this rule, well, that's -2.5 minus 1, which is -3.5, is 2 between -0.5 and -3.5. Not even close. So that means that the IVT does not apply on this one. For this problem, we're trying to use the Intermediate Value Theorem to show whether there's a c value on the interval from 0 to 1, so an x value, where f of c equals 0 for this function. So to use the IVT, we have to start by verifying continuity. This is a polynomial, so that means that it's continuous everywhere, including the interval from 0 to 2. So we're good on that score. Now we have to plug the beginning and ending x values into the function to see the beginning and ending y values, and we'll figure out if 0 is between those y values. So f of 0, the first y value, that's just going to be 0 minus 0 plus 2, so 2. And then f of 2, that's going to be 4 minus 8, so -4, plus 2 is -2. Is 0 between 2 and -2? It is. So in this case, the IVT applies and guarantees that y equals 0 somewhere on this interval. On this problem, we're trying to figure out if the IVT shows that there's a c value where f of c is 4, somewhere between the x values 3 and 8 on this x plus 7 over x plus 3 function. So to use the IVT, we have to verify that we are continuous on the interval in question. And for that, we look at discontinuities. This function is only going to have one discontinuity at x equals -3. That's giving it an infinite discontinuity, an asymptote. Since we have a discontinuity at -3, we're okay because that's not on the interval from 3 to 8. So that means we're continuous everywhere else, and we can keep going with the problem. Next, we're going to plug in the x values 3 and 8 to get the beginning and ending y values. We'll see if 4 is between those when we get them. So f of 3, that's going to be, let's see, 3 plus 7 over 3 plus 3, so 10 over 6, which comes out to 5/3. Now plugging in 8, we've got 15 over 11. And we're asking, is 4 somewhere between 5/3 and 15 over 11? And you might be a little bit confused on here because we've got these fractions, but let's just think about this. How many thirds is 4? Well, 4 is 12/3, and 4 is 44/11ths. So there's no way that 4 is between these. This is like 1 point something. This is also 1 point something. Definitely not something that 4 could be hiding between. So because 4 is not between those y values, IVT can't guarantee anything and does not apply on this problem. On this problem, we're trying to see if the intermediate value theorem shows the existence of a c such that f of c equals 1 for ln of x on negative 2 to 8. So basically, is there a y value of 1 that we're guaranteed to find on this function between these x values? So because we're using IVT, we have to verify continuity. The ln function we know is undefined when x is less than or equal to 0. Does that affect us on this problem? Well, it does, because there's some x values in here that are less than or equal to 0. Because ln of x is undefined on some of those x values, we would say that we're not continuous on the whole interval, so the IVT does not apply and cannot guarantee anything on this. There might still be a c value that makes all this stuff equal 1, we just can't guarantee it because of the interval they gave us. On this problem, we're trying to see if the IVT shows the existence of a c value such that f of c is negative 7 for this function between the x values 4 and 6. Since we're using intermediate value theorem, let's check for continuity before anything else. The function type here, this is an exponential function of some sort, and exponential functions we know are continuous everywhere, so we're good for the interval from 4 to 6, or anywhere else. So next we check the beginning and the ending y values. So we're going to plug the x values 4 and 6 into the function and see where this thing begins and ends. So plugging in 4, f of 4, that's like having negative 1/4 to the negative 2 power plus 2. And what does all that come out to? Well, 1/4 to the second power would be 1 over 16. Negative second means that's 16. We have a negative out in front, so that's all negative 16 then plus 2. So that's negative 14. Now we're plugging in 6, so that's like having negative 1/4 to the 0 power plus 2. We know that anything to the 0 is 1, but we got to be careful because this negative is happening after we apply that exponent. So this is really negative 1 here plus 2, which comes out to positive 1. All right, is negative 7 between negative 14 and 1? It is. Therefore, the IVT guarantees that we can find a negative 7 somewhere on this interval. The IVT applies, and we're good. On this problem, let f be a function such that f of 1 is negative 2, f of 5 is 7, which condition ensures f of c equals 0 for some c value in the open interval from 1 to 5. All right, so we're basically talking about the language of the intermediate value theorem here. We've got 2 points, and we're trying to show that some in-between y value is actually in between these on the open interval from 1 to 5. So in order to use the intermediate value theorem, that requires that we have continuity on a closed interval. That is always the condition we check for when invoking the IVT. So the answer choice that actually has that is answer choice C. F is continuous on the closed interval from 1 to 5. So right away, answer choice C is what we're looking for. But you might be wondering about some of these other answer choices and why they aren't where it's at. So this first one, answer choice A, this is talking about the area between the x values 1 and 5 existing. And that by itself doesn't necessarily mean that we're going to hit a y value of 0. It doesn't really have much to do with it. And it could be true, this is the most important part, this area could actually exist even if we have a jump somewhere on this interval. Same thing with B. F is increasing on the closed interval. Well, that's nice, except you could have a jump and still be increasing, right? We could jump from, say, negative 2 all the way to positive 1 and then keep increasing, and B would be satisfied. And now choice D, F is defined for all values of x. Well, that's also nice. However, you can have jumps where one of the parts of the jump has a solid dot. So because A, B, and D could still be true with jump discontinuities and discontinuities in general, that means that only answer choice C satisfies the IVT. For this problem, we've got this weird function x plus cosine of x over x plus 3, and we have a bunch of statements about it exists, does not exist, horizontal asymptotes, and intermediate value theorem. Just a little potpourri of everything. So let's start with statement 1. They're saying the limit at negative 3 does not exist because the right-sided limit, as we approach negative 3 from the right side, we go to positive infinity. taking a look here, we notice that there is going to be a vertical asymptote at -3. That zeroes out your denominator. So that means there's some kind of infinity involved as we come from the right side. Now, it could be positive infinity, or it could be negative. To figure out which one it is, we're going to test a x value that's pretty close to -3 on the right side, such as negative 2.99. Let's test out negative 2.99. Now, if we plug negative 2.99 in this function here, it's going to make the denominator positive. Anything to the right of -3 is going to make the denominator positive. How about the numerator? I'm not sure what cosine of negative 2.99 is, but I know it can't be more than 1. And if you do 1 plus negative 2.99 here, overall that's going to come out negative upstairs. So you've got a negative over a positive, giving us an overall negative result if we plug negative 2.99 or anything close to that into the function. Well, if we're negative that close to the asymptote, that must mean that we're going to negative infinity rather than positive infinity. So option 1 is no good. All right, moving on to option 2. Graph has a horizontal asymptote at y equals 1 because the limit at infinity is 1. So if we take the limit as x approaches infinity, we're going to choose our champion on this one. Fastest growing function in the numerator is x. X keeps growing. Cosine just bops back and forth between negative and positive 1. And in the denominator, x is also the fastest growing function. So we have x over x as x approaches infinity. And we can just reduce that to 1. So that ends up actually being true. Now for option 3, IVT guarantees a value of c on the interval -4 to 0 if g of c equals -1. So before you go ahead and plug in numbers to this crazy function, let's check to see if we even have continuity on this interval. We have that vertical asymptote at -3. And -3 is on the interval from -4 to 0. The IVT guarantees nothing if there are discontinuities on the interval. So for that reason, the IVT doesn't apply here, and the only true statement was statement 2, so that would be answer choice D. For this problem, we have a function f that's continuous on a closed interval from 0 to 2, and they gave us some table values for this. They want to know what value of k guarantees that f of x equals 1/2 has two solutions between 0 and 2. So this can be a little bit tricky, but I think it helps if you graph what we have out. So we have the point 0, 1. We have the point 2, 2, somewhere over here. And we have, I guess you could draw a horizontal line to represent f of x equals 1/2. And we're essentially asking what value of k, there's some point with a 1, something that guarantees we're going to hit this line twice. So just thinking about intermediate values here, the IVT says that if a function is continuous on an interval, which is important because they told us this function was continuous on this closed interval, it's guaranteed to hit y values that are between the starting and ending y values of the interval. So basically, if we want to have two solutions, we need to get a k value that creates two intervals where 1/2 is between the starting and ending y values of those intervals. To put it simply, this f of x has to drop below this line in order to hit it twice. So let's go through our different choices here and see what accomplishes that. Let's say that k is 0. We would have the y value 0, so this would be 1, 0, which would be right here on the x-axis, and we would indeed have to hit that line twice with a continuous function. So this is looking like a pretty good answer choice, but let's look at the others here. If we have a k value of 1/2, well then we would be hitting the line guaranteed once, but no guarantees on hitting it again before we get back up to 2, 2. And if we have 1, well that's up here, same thing with 2 and 3. So although it might hit the line twice or more times, we're not guaranteed anything if we're not guaranteed that we get below this f of x equals 1/2 line. So at the end of the day then, k has to be 0 out of these answer choices to make this happen. So choice A. For this problem, we're given f is a continuous function on the interval from 3 to 6, and we're given some function values here, and we want to know what the intermediate value theorem guarantees. All right, so I think it's good on this if you graph these out or sketch this out just to have a visual. So we've got the point -3 comma -1. That's somewhere down here. And we also have 6 comma 3 somewhere over here. And we want to know what IVT guarantees if we have a continuous function between these 2 points. We don't really know what's going on between them, but we at least know that there's no breaks in here. So going through our answer choices, f of 0 equals 0. Well, we're guaranteed that we're going to hit the x-axis, the y value 0, somewhere between the y values -1 and +3, because this is a continuous function, but we're not guaranteed as to exactly where that's going to happen inside the interval, just that it happens somewhere. So we only know that f of x equals 0 somewhere, but not specifically that it happens at x equals 0. So moving on to the next one, f prime of c equals 4/9 for 1c between -3 and 6. So if you haven't gotten to this material yet, this f prime is basically talking about the slope of the f function. And although this may be true, it has nothing to do with the intermediate value theorem. So since IVT says nothing about slope, this would not be a good answer to this question. Moving on, -3 less than or equal to f of x less than or equal to 3, basically saying that the y values stay between -1 and 3, inclusive, in between this interval. Well, we know that we're going to hit all the y values between -1 and 3, but we're not guaranteed that we won't stray outside of there. Our function could go up and then come back down and still be continuous. So since you could go outside this range and come back in, this is also not a good answer choice. At least based off the intermediate value theorem, it makes no guarantees about what's not in your interval. Next, f of c equals 1 for at least 1c between -3 and 6. Well, the y value 1 is between -1 and 3, so this is guaranteed by the IVT. We have to go through y equals 1. But let's just look at our last answer choice to make sure that D is really the best answer. So f of c equals 0 for at least 1c between -1 and 3. Well, we are going to hit the y value 0 somewhere, but this is not the same interval that we had the continuity on in the beginning. It's kind of like they mixed up x and y values on this one. Since we're not using the whole interval, we're not guaranteed that we hit 0 between -1 and +3 for the x values. We're guaranteed we hit it between -3 and +6, but this interval is too small. So choice D then is the only one that works here.